So we're going to start in on a new chapter, and the topic of this particular chapter is linear momentum. Okay. Linear momentum is what Newton called the quantity of motion. Okay. And the way the momentum is defined is that it's defined as the product of the mass times the velocity. So what we get is that this is a lowercase vector p. And it's kind of hard to tell case on white paper, unlined paper. And so this is going to be our linear momentum vector. And what we'll find is that the reason they use the adjective linear is because in the next chapter, I believe we're going to have angular momentum. Okay. This, of course, is the mass of the object, and v is the velocity of the object. So, and again, as I have stated before, since mass is not negative, then what happens is that the direction of the velocity is the direction of the linear momentum. Okay. So those will always be in the same direction. We go in and we look at our SI units of momentum. They're the units of mass, which are kilograms, times the units of velocity, which are in meters per second. And this is not a derived unit. I mean, so it's the unit of momentum, but there's no derived unit for this quantity, which is somewhat interesting because it plays a fairly important role in physics. But not. I guess it wasn't needed until chapter 9 to discuss motion. But so it's a little interesting, that it doesn't happen to have a derived unit. And what we'll find is that technically Newton's second law was defined in terms of momentum. Okay. And so the way Newton actually wrote the second law is he wrote that it was that the net force is equal to the time derivative of the momentum. Okay. And then you might be going, well, how is this related to F equals ma? Okay. Now, how do we get that relationship there? Okay. And the answer is that, well, if we go in and put in the definition of momentum into our derivative, then we take the time derivative of the mass times the velocity. Okay. And what this gives us is the time derivative of the mass, by the product rule or the Leibniz rule. You take the derivative of the first times the second plus the first times the derivative of the second. Okay. And when we look at this time derivative of the velocity, well, then that is our acceleration. That is a. So you can see ma. I mean, it's right there. Okay. But then there's this, whole other term that we have. Okay. So what we're at that the net force is equal to the time derivative of the mass times the velocity plus the mass times the acceleration. And so then what you get is that essentially, if this term is 0, then what you get is F equals ma. Okay. And so we can look at this. This is a product of two terms. The time derivative of the mass times the velocity. If we set that equal to 0, then that implies that either the first term is 0 or the second term is 0 or they are both 0. Now, this one is a little problematic because this is the velocity, the instantaneous velocity. And so what you get is that if the velocity is 0, then essentially what we have is in this instance, we have no motion. Not that it started at rest, but that there was no motion at all because this is the velocity in the process. And so then if we don't happen to have any motion, then what that leads to is that leads to static equilibrium type of problems. And with static equilibrium problems, then the formula for those was that the net force was 0. So that was the condition for static equilibrium. And so then it doesn't matter if it was ma or the time derivative of the momentum. I mean, if the net force is 0, then it's irrelevant in terms of which version we have. And so then what we're left with is essentially this condition here. And if we look at this, what it says is that the time derivative of the mass is going to be 0. And so that implies what about the mass? Well, will give us a 0 time derivative for a quantity. What does that imply? Mass is indeed a scalar, but that doesn't imply that the time derivative of every scalar quantity is 0. Yeah, Brandon has it. That means that that's constant. So if you have a constant quantity, then the time derivative, the derivative would be 0. So if this is constant, then what we get is we get that this term is 0 and we obtain F equals ma. Okay. And so what we're seeing is that essentially this, what we learned before as Newton's second law, was really just a special case. And if we think back in terms of all the problems we've looked at, in any of those problems, did the mass of the objects ever change as it, moved along, kind of things? And the answer is, well, no, and so then what we can try to think about is, well, when would we have a changing mass on our object? So when would F equals ma not apply? So thus F equals ma is a special case of our Newton's second law. When we have a constant mass. Well, let's try to think of some examples where the mass of the object would not be constant. What do you think? What objects could we not use F equals ma in order to analyze? Or situations or whatever. That's like the classic example is the one your mom said. It's the when you have a rocket motion. When we do rocket motion, then as the rocket, takes off, then it burns through lots and lots of fuel. And in fact, if you look at most rockets, it's, a bunch of big fuel canisters and a tiny little payload, you know. And then to make matters even worse, once you empty the canisters, the fuel, then they jettison them. I mean, so then you drop even more mass. I mean, so that is the quintessential motion. So is rocket motion. So that's the number one thing. Okay. So for rocket motion, the mass decreases. Or now the other one that usually often comes up would be if we had like a snowball that rolls down a hill and then gains snow as it goes. And so that's an interesting example because then in that case the mass increases rather than decreases. You could also have things like a train car that has an open top, and then if it rains or it snows or whatever, it could gather water or gather snow and increase the mass of the object. But I'm going to do the snowball. Where it rolls down a hill. Where the mass increases. Okay, so for these cases, then what you need to be careful with is F equals ma is not valid. But the net force is the time derivative of the momentum is. Okay, and so that's one of those funny things is we have to, be careful. Is that if the mass of the object is going to change, then we actually have to use this new version of Newton's second law, the time derivative of the momentum, in order to solve or work on those problems. However, if mass is constant, then we can use the version that we've been working with, all along. So now what we're going to do is if we go in and we take a look at our new version of Newton's second law, then what we can note is that if the net force is 0, so kind of like our static equilibrium type of problems, if the net force is 0, then what you get is that 0 is equal to the time derivative of the momentum. And so then this implies that our momentum has to be constant. Right? And so what this is referred to as conservation of linear momentum. Okay. And what you get is that this is our condition for the momentum to be conserved. Okay. So it's a conditional conservation principle, just like mechanical energy. was a conditional principle as well. You know, where the way that I always presented it was that if the non-conservative forces didn't do any work, then what we end up with is then the mechanical energy will be conserved. And in the way the book did it, it was a little more, you know, convoluted, but it gets you to the same place. So it's an equivalent kind of thing. Okay. So these are both conditional conservation principles, but then we have that global conservation principle of total energy is always conserved. But the problem with total energy is you have to account for all the other forms of energy, you know, uh, vibrations and sound and thermal energy and, you know, all sorts of good fun stuff like that. Now, what we're going to find is that while we can get conservation of linear momentum, we're not usually interested in analyzing this in terms of a single object. To analyze the motion of a single object. Okay, because if we look at this in terms of our principle that we go, oh, the initial momentum is the final momentum, and so then what you get is that this will be the mass times the initial velocity is the mass times the final velocity, because for most objects the masses don't change, and so really what you get is that the velocity is constant is the implication. You know, now if you have a changing mass, then we get things that are a little more interesting, but again, usually we don't have those. I mean, so those are kind of like special cases in some sense. So what we have is that if our mass is constant, then what you get is you get that the velocity is going to be constant. And so so it's either not moving or it's moving at a constant velocity, and neither of those do I really need this technique in order to analyze. I mean, this is like we can do other things to get and analyze that motion. Okay. So, okay. And so then what happens is that we're going to go in and very similar to what they talked about in that energy chapters, we're actually going to start looking at systems. Okay. And so this is going to be the new version. So we are interested to look at systems of objects. Okay. And so what they do is they go in and they will define what they call the total momentum. Okay. And so usually to kind of help me out, I usually kind of put like bars on the bottom so I can tell that's like a capital P instead of a lowercase p. I think that's, let me double check the notation in the book here real quick. I think that's the notation our book uses. Each one uses slightly different notations. Can be a little annoying. Systems. No, they do a lowercase p total, but I'm probably going to just put the little bar on the bottom anyways. And so what you get is that this is the sum over all of the objects. So 1 to n over the objects of their individual momentum. Okay. So what you get is this is momentum of object 1, vector added to momentum of object 2, all the way out to the, momentum of the last object. You just vector add those together, okay? And so they go ahead and define this total momentum. Therefore, what we get is when we go in and take the time derivative of this total momentum, then what you get is that this is the time derivative, and I'll just write it in the more standard way. You all know summation notation, but we'll just write it out like this. And so then what you get is this is the time derivative of the momentum of object 1 plus the time derivative of the momentum of object 2, plus the time derivative of the momentum of the nth object. And then by Newton's second law, this is our net force on object 1 plus the net force on object 2, added all the way up to the net force on object n. Okay. And when we vector add all of these together, then what you get is the total net force over all of the objects. And that's equal to this time derivative of that total momentum. So what you get is Newton's second law for the system is Newton's second law for the objects. I mean, so it has the same form. So you get essentially the same form of our Newton's second law. And then we can go on and we can talk about the fact that, well, if the net force over the system is 0, then the momentum of the system is constant, and we have conservation of linear momentum type of things. So then we can go in and repeat what we had done for the single object, but now for our system of objects. So again, we have conservation of linear momentum for the system. Our system of objects. And again, this is our condition. Okay. And so the one thing that we'll need to know is that one thing that is different between conservation of mechanical energy is that this is a vector condition, and this is a vector conservation principle. Okay. So the condition is a vector equation which we solve vector equations by breaking them up into components. Okay. And so what's interesting is that in one component direction, we could satisfy the condition and conserve momentum in that direction, but in the other direction, it might not be conserved. So that's kind of an interesting thing to think about, is that, we might have conservation of linear momentum in, let's say, the x direction, but not in the y direction in a process. So, I mean, I think that's, like I said, that's kind of one of those interesting things. It's not like a scalar quantity where it's true everywhere kind of things, but it could be one component direction, but not another component direction. Okay. Let me get rid of this because I continued on. Go. All right. So, like I said, I think that's kind of an interesting piece, is that it's possible. And so one thing that we should probably talk about is in terms of the relationship of conservation of linear momentum to Newton's third law. Okay, so y'all remember Newton's third law? Good, good, good. And so with Newton's third law, we stated that, all forces come in pairs. That are equal in magnitude. And opposite in direction. Okay. And what we argued at the time that we studied third law is that they don't usually cancel or sum to zero. And the argument was that they acted on different objects, right? On the box, by the table, on the table, by the box, right? For like the normal force when we put a box on the table, okay? But what'll happen is if we go in and we include all of those objects that are interacting to create the forces within our system, then when you sum over the whole system, they will cancel out in pairs. If we include all the objects that are interacting, into our system, Yeah. Yeah, if you include all the bits that are interacting, then you're guaranteed by the third law that they are equal magnitude, opposite direction. And then when you sum over all the objects, you get zero. You're guaranteed conservation of momentum, you know. But the drawback is you might have to include things you didn't want to include in your system, you know. So you might need to include the analysis of, you know, things that you weren't really interested in order to get the parts that you are interested in. So there's a little bit of a trade-off, right? Because you've got to include like everything in the universe in order to gain your conservation of momentum. That might be terribly useful in the end, you know? So, but in principle, that's how it works. And so a lot of times when people talk about conservation of linear momentum, they talk about it hand in hand with Newton's third law because of this. Okay, for our system. I'm going to try to be specific about that. Hmm. It's more like a sigma. And so what we end up with is we end up with things like our, you know, the initial total momentum is our kind of final total momentum. And of course, the way we handle this is we handle this by components. Okay. And so you would do, you know, X's and Y's, let's say. I mean, you could also do Z's, but I highly doubt we'll see those, but that's all right. In general, we could see those. So this will be our initial, you know, X component of the total momentum. I don't know what order to write the subscripts. So, and then the final X total, probably should have put the total further up. Hopefully y'all will be okay. And then we'll do the initial Y component of the total momentum is the final Y component of the total momentum, like so. So yeah, we do X's and Y's, we do them by components. And then if we want, we can go in and write down our, you know, kind of the equations that we get. And with this triple subscript stuff, I'm going to show you a different way to note our initial and final quantities. And so then in our, you know, X direction, and in the Y direction. So the way that I usually do this is, let's assume we only have two objects in our system. And I think we'll probably be limited to like 2 and 3 objects predominantly anyways. And so then what we'll get is you'll have the mass of object 1, and as a general rule, the masses of our objects aren't really going to change. And we have the X component of that velocity of object 1. So this is the momentum of object 1 plus the mass of object 2 times the velocity, the X component of the velocity of object 2. And so this is the before, and then the after, what they'll do, or what I generally will do, is put a prime on these. Okay, and so the notation is that if we have no prime, then these are initial. And if we have a prime on the quantities, then these are final. And notice I didn't prime the masses because as a general rule, they don't change. So, okay. And that's nice because now the prime is a superscript rather than having, you know, more than 2 subscripts. I think having 3 subscripts is kind of eh. You know, I try really hard to avoid having that many subscripts. We can't really avoid that when we do like those relative velocity kinds of problems. We kind of have to have that many subscripts. But beyond that, I try really hard not to end up with quite that many. And so then if we come in, we'll have the mass of the first object times the y component of that velocity plus the mass of the second object times the y component of its initial velocity is the mass of the second v2 prime y, mass of the second, v2 prime y, sorry, these have to be ones. Okay, so there we go. So these are, you know, and again, I only wrote it out for, you know, 2 objects within our system. If there were more, then you'd add more terms. So, and I guess that's really the way that I learned was that, you know, this is a pretty common notation. You see it in a lot of the textbooks. This, you know, no primes and primes as initials and finals. And especially once you get into the momentum chapter, then this is pretty common. So I guess I tend to like this because this is the one that I learned when I learned physics. So.